All right, well, I think we're going to get started. Let me just make sure my own kids are on. Jonathan and Alyssa, are you guys on? Hi. Okay, so we're going to get started here. So you guys remember, so last week we talked about how the world was round, right? And we talked about there was another thing that really was getting in the way of physics before physics could really get going. It was a thing about the conception, people's conception of the universe. You know, part of it was that people thought the Earth was flat, but there was another reason, another idea that was really hard to get out of people's minds and really prevented physics from getting going. Does anyone remember what that idea was? Jonathan?
That the Earth was the center of the universe.
Right, perfect. And Jonathan, I'm happy to say that your audio works today. And you guys, why was that? Why did people think it was the center of the universe? I just want to make sure you guys are clear on this because this is kind of an important point.
Because they saw the stars move over them and the sun move over them and the moon, so they thought that they were the center.
Exactly. Everything they looked at in the heavens was moving around them. They don't feel themselves move, and therefore, you know, they have to be at the center and everything's moving around them. Okay, so now, even though it was, you know, 200 years BC when Eratosthenes proved that the world was round, it would not be until the 1500s or 1600s when people started talking about maybe the Earth isn't the center of the universe. Now, here's the deal. For 1500 years, people would look up at the heavens and they would see the stars move, and that was easy to explain with, oh, well, it's all just going around us. But the planets move too, and the planets move in a very peculiar way. And people were trying to figure out ways to explain the movement of the planets, and it got really complicated and ugly. And I've kind of gone back and forth. Is it better to teach what the planets are doing so that you feel like you understand why people needed to somehow come up with an explanation for how the Earth isn't the center of the universe? But the movement is complicated. And it probably takes about 3 hours to explain. And I thought, oh, what if I lose people in that? So I'm just going to tell you that around about the time of the late 1500s, there was a guy named Copernicus. And he said, this is just, how people have come up with these crazy ideas to explain the movement of the planets. It doesn't make any sense. The whole thing would make sense if the Earth and all the other planets revolved around the sun. Then the motion of the planets, as seen from the Earth, would all make sense. But he just had no way of explaining why we don't feel the Earth move. And then came along in the 1600s came Galileo, and you guys have all heard about him. He's the guy who dropped the rocks off the Tower of Pisa. It probably actually didn't happen, but it's a great story. But he did experiment a lot with falling objects. Yes, Jonathan?
It was hard for Copernicus because over 1,500 years, like, it kind of became part of the church.
That's a great point. So this is a great point. So the church, the Catholic Church, which was the power at the time, they had sort of a vested interest in saying that this was, this was the way the world works. They had scriptures. I don't know if any of you guys know about the Old Testament, but there's a passage in Joshua where he commands the sun to stand still, right? And it was really hard for the church to let go of that. Besides which, they thought, well, the Earth was created for man, and so, of course it has to be the center of everything. And that was really hard to let go of. And in fact, so I'll come back to this in a little bit, but Galileo, he liked the idea of Copernicus, and so he had to come up with a way to explain why we don't feel the motion of the Earth. And he was really brilliant because this idea, although when I explain it to you guys will be like, well, that kind of makes sense, I guess. But it has some implications that are really profound and maybe not intuitively obvious. So, and Copernicus did this all because he liked the sun-centered model of the universe so much better. It was so much more elegant, explained things so much better. He actually published a book. It's really an interesting story. I'm just going to summarize it here. He published a book wherein he talked about the sun being the center of the earth. He had a very good relationship with the Pope, and at first the Pope was telling him, yeah, go ahead. I mean, it's an interesting idea. It's, you know, theory or whatever, but go ahead and publish this book. And then a bunch of advisors to the Pope said, this is totally dangerous. Don't do this, Pope. And so the Pope said to Galileo, okay, look, you know what? Just to keep everybody happy, I want your book to argue both sides, right? I want you to have, you know, present the evidence for the earth as the center of the universe. I want you to present the evidence for the sun as the center of the universe. Galileo did this, but he was so angry about it that he actually had, his book was a conversation between three people. One guy was very obviously intelligent and arguing that the sun was the center. One guy he actually named Simplicio, which is kind of like simpleton, which is a dumb person. And a lot of people who read, and that person was arguing that the earth was the center of the universe. And to be honest with you, a lot of people, when they read this, they thought the Simplicio was actually making fun of the Pope. Like they thought that Galileo had intended Simplicio to be the Pope himself. And I don't know if Galileo meant that or not, but that's what people thought. And so this landed Galileo in a lot of trouble. He was actually placed under house arrest for the rest of his life, told he couldn't be, he was actually showed the instruments of torture that we're gonna torture you if you don't renounce this. He finally struck a deal. He said, I'll remain in house arrest for the rest of my life. I won't publish any more books. And I just will keep quiet. And so he wasn't tortured. He actually did write a book, and he snuck it out he had his daughter wearing a dress sneak out his book under her dress, and it was published after his death, which talked more about this idea. But I've decided we're just going to skip all the motion of planets, and we're going to talk about how it is that you get to explain that the Earth is not the center of the universe, and yet we don't feel it move. Okay, so here's Galileo's big idea. Galileo's big idea is, well, let me actually go about this a little slightly different way. So you guys, when you see a jet airplane overhead, does anyone have any idea about how fast it's moving? Just throw out an idea. Pardon? 700? Pretty close. So yeah, it's usually about 600 to 650, somewhere in that range. Jonathan? Your audio, we have no audio on you. You're muted. Okay, let me unmute you.
I just gonna say around like the sound barrier.
Right, so it's very expensive. It uses a lot of fuel to go faster than the speed of sound. You have to have a special airplane construction so it can withstand that. So passenger airplanes go about 90% of the speed of sound, which is somewhere in the 600 to 650 range. Okay, so you're on an airplane, you're traveling about 650 miles an hour. How much does a car, when you're on the freeway, about how fast are you going? Lisa, how fast are you going? Oh, hold on. Are you raising your hand, Alyssa? Okay, I can't hear you. Oh, unmute. Here we go. How fast are you going?
Probably about like 45.
45 is kind of a fast road in town, but not on the freeway. Go ahead, not Courtney. What's your name?
Courtney.
Oh, I'm sorry, Courtney. Oh, you've grown a lot. Okay, tell me.
65.
65, that's a good speed limit. So, you know, some states it's more, some it's less. So here's my question to you, Courtney. I'm going to stick with you for a second. How fast are you moving now?
Probably about the same speed as the Earth is moving.
Good answer. Good answer. Who else has another answer? How fast are you moving, Jackson?
It's like It's like 3,000 something miles per hour, right?
Sure. This is actually a trick question. So
Really?
your audio cut out. The only thing I got was relative, and I think, Jonathan, what you're trying to say is relative to what? So here was Galileo's big idea. Galileo said, you can't say how fast you're going. You can only say how fast you're going relative to something else. So if you were to ask a physicist, how fast does an airplane fly? He would tell you 650 miles an hour. But if you said, as a physicist, how fast does an airplane fly? He would say to you, relative to what? Because there's no such thing as, in physics, an absolute speed limit, because you can only reference your speed relative to something else. Someone have a question? Okay, so why is this important? So the reason why it's important is that there is no unique part of the universe. It's not the Earth, not the sun, not the center of the Milky Way. There is no center of the universe. There's nothing that you can reference and say, this is exactly how fast I'm going. You can only say, I am motionless. Steve Cannon is motionless relative to the Earth. Okay? All of you guys are motionless relative to the Earth. Or you can say, I am orbiting the sun at X number of miles per hour. And I was meant to look it up and I forgot to. I'm orbiting the sun at X number of miles an hour. Or you can say, I'm orbiting the center of the Milky Way at X number of miles per hour. That works too. Or you can say, well, our galaxy, the Milky Way galaxy, is orbiting what's called the local group, which is a local group of galaxies, and they're all orbit each other. It's called, they move under each other's influence of gravity. And you could say, relative to the center of the local group, I'm orbiting at this speed. And you could say that too. But you can't say, I'm moving at 20 miles an hour. In physics, that has no meaning, literally has no meaning. So why is this important? So let's go back and talk about an airplane. So raise your hand if you've been on a jet airplane. Okay. So for those, so Rasmussen's, you have not, and Bailey, you have not, is that right? I didn't see you raise your hand.
What do you mean? Just like on an airplane in general?
Yeah, have you been on an airplane before?
Yes.
Okay, everyone has. So the airplane's going 650 miles an hour. And the stewardess has a cup, a can of soda, and she goes to pour the can of soda into the cup. Does she have to hold the cup super far back because the soda is going to go backwards at 650 miles an hour? No. Let me ask you this. Does she do anything differently when she pours that can of soda than you were doing if you were standing stationary on the ground?
No.
No.
Other than watching out for turbulence.
Oh, great point. Excellent point. Okay, we're going to get to that in just a second. So the fact of the matter is despite the fact that when I've been talking to you guys, I've said at least a dozen times, you can feel motion. You can't feel motion. There's no way to feel motion. What? You can't tell whether you are moving, whether you're moving on a jet airplane or whether you're standing on the ground. You can't tell that. The only thing that you can say is relative to the airplane, I am motionless. My can of soda is motionless relative to the airplane. It's motionless relative to me. My cup is motionless relative to me. Therefore, I can pour it, and it's going to pour it in exactly the same way as it would if you were on the Earth. So in physics, from a physics point of view, if you're on the airplane, you can actually say, in the laws of physics, it's perfectly legal to say this, you can say, I am motionless, and the Earth is rotating, is moving past me at 650 miles an hour. And that's a perfectly reasonable thing to say. Now, you all say, well, no, really, the Earth is motionless and the airplane's moving. And a physicist will tell you, no, it's not. that is, and in physics, we talk about this thing called a frame of reference. And a frame of reference means what you as an observer are I should have looked this up, a good definition of frame of reference, but it means you as an observer, what it is you see, what you experience, that's your frame of reference. And in physics, with one exception, all frame of references are equally valid. We say that they are on equal footing. We say that they are, I don't know, there's another word people use and I'll come up with it in a second. But as an observer on the airplane, it is your frame of reference is that airplane, and it's perfectly legal for you to say, I am motionless and the earth is moving beneath me, okay? And as someone who's sitting on the earth, it's perfectly legal to say, I am motionless and the airplane is moving past me. Now, so let's talk a little bit about frames of reference, okay? And I'll come back a little bit later to the one exception of when you can't, when your frame of reference isn't equally valid. But right now, we're gonna do this share screen. Let's share screen. We're gonna go to this whiteboard. All right. So let's see if this works. Shoot, I wanted this to be a different color. How do I change color here? This is, so this, oh, format, there we go. Yeah.
There's a thing in the corner that's like a little pen. I think you got it. Never mind.
Okay. So what I have here is I have a river. Okay. And the water in this river is moving at 5, oops, uh-oh, let's try this again. 5 miles per hour, okay? I also have, standing on the bank of this river, I have an observer, and he is motionless relative to the ground, okay? And then I also have in the water, I have someone who's just, the only thing that's sticking up is his head and his arms, and he's not swimming, he's just being dragged along by the current. How fast is the guy in the water moving relative to the guy on the ground?
5 miles per hour.
Good. Does everyone see that? Because the water is going at 5 miles per hour, and he's just being dragged along for the ride. So he's going the same, relative to him, how fast is the water moving?
Nothing, not at all.
0. Okay, good. So this guy is perfectly valid for him to say, well, I'm not moving. I'm just, the water around me is not moving. Nothing's moving relative to me. It's just this guy on the land. He's moving that way at 5 miles an hour. And he's perfectly able to do that, okay? Now, if the guy, let me erase this for a second. So if this guy, instead of being dragged along by the current, what if he starts swimming against the current at 2 miles per hour? Whoopsie. Okay, he's swimming against the current at 2 miles per hour. How fast is he moving relative to the water?
3 miles per hour.
Well, not relative to the water, because he's swimming, when he was holding still, he was moving, not moving relative to the water. Now, relative to the water, he's moving 2 miles an hour that way. Does that make sense to everyone? Why don't you guys unmute yourself so you can tell me if it makes sense or if you're not clear?
Yeah.
It makes sense.
Okay, good. Okay,
Yeah.
now here's the question. If he's moving 2 miles an hour relative to the water, and the water's moving 5 miles an hour in this direction, how fast is he moving relative to this guy?
7 miles per hour, right?
Not 7. Now, if he was swimming with the current, he'd be moving faster than the water. So we would add this plus the 2, and we get 7. But since he's swimming against the current, he's actually almost keeping up, with the shoreline. So he's going at 5, because we'll say that going to the right is a positive number. He's moving to the left, so we'll call negative, moving to the left a negative. So he's going 5 minus 2 equals 3 miles an hour relative to this guy. So he's being swept along with the current at 5 miles an hour. He's swimming against the current was 2 miles an hour. That leaves 3 miles an hour that he's moving relative to this guy. Now he can say this guy's moving to the left at 3 miles an hour, or this guy can say the swimmer is moving to the right at 3 miles an hour. It doesn't matter. These are called frames of references. Now, what we've done here is we've jumped from one frame of reference to another using what's called the Galilean transformation, named after Galileo. Galileo simply said to move from one frame of reference to another, all you have to do is you have to add their velocities. Now, if their velocities of the frames of reference are in opposite directions, then you have to subtract. But an easy way to say that is, well, you just assign, stuff going to the right is a positive number and stuff going to the left is a negative number. But the point is that he exactly nailed this in saying that you can jump from one frame of reference to another, and you can simply add or subtract the velocities, and you can jump from one frame of reference to another, and you can choose the frame of reference that suits you best. And with this one exception that I'm going to explain in a little bit, that's a perfectly legal thing to do in physics. And when I say it's a perfectly legal thing to do, what I really am trying to say is, that the laws of physics all work the same, no matter what your frame of reference is. Now, I'm going to take a little side note that I hope you'll find interesting. And it's not that I expect you to understand what I'm about to tell you, okay? If there's some people who really just love physics and want to someday learn about Einstein's theory of relativity, I would be happy to take a session and talk about that. It's a little complicated. But I'm just going to tell you a little bit of a historical note and tell you how important this concept is. Okay, so in the late 1800s, there was a guy named, last name of Maxwell, and he was a mathematical genius, and he wrote down a set of mathematical equations that describe electricity and magnetism. And in order to keep his equations mathematically correct, he had to add a term. He didn't know why. He just said, well, in order to make the math equation internally consistent, I need to add this little piece of math here. Did someone say something? Okay. Well, physicists looked at those equations and they said, that last term, it looks like an equation for a wave. What's that, Maxwell? And he said, I don't know, I just put it in there because that's what it took to make the math all balance out. People started saying, well, it looks like a wave. And after a while, it became clear that these laws, these mathematical laws, were describing not just any old wave, but light, which is a wave. And people said, wow, that's really crazy. For the first time ever, someone was just doing math and they came up with this, an equation that described something, and it taught us that it's about light. We didn't even know that light was, electromagnetic waves, but that's what they are. It was crazy. It was like just out of the math, he pulled this out, Here's the problem, is that in the equation itself tells you what the speed of light is. And people started wondering about that. They started being like, well, wait a minute. We've, for 250 years, believed that all speed has to be relative to something else. So, and that we believe that there's no universal reference point. You can't say, oh, the center of, I'm moving this fast relative to the center of the universe. You can't say that. There's no universal reference point. Every frame of reference, with this one exception that I'll get to later, is perfectly valid. And people start saying, that's really weird because it's in the equation. It tells how fast light moves. And so people started coming up with this idea, well, maybe we need to give up on Galileo. Maybe we need to say that there is, you know, a universal reference point from the universe, and all speeds are measured from that. And that's why light has its speed given. So Einstein hated this. He said, I am not giving up on Galileo. What if everyone can measure the speed of light and it's always the same no matter what direction they're moving or how they're moving or what they're doing? It's always the same. Now, this makes no sense, okay? It would be like, you know, if a guy in a boat floating along in the river measures the swimmer going 5 miles an hour, and the guy in the boat is being dragged along with the current, and then some guy on the shore also says, well, the swimmer's going at 5 miles an hour, but, you know, I mean, Galileo said you can hop from one frame of reference to the other by adding and subtracting velocities. And Einstein's like, well, what if, just work with me here. What if everyone measured the speed of light to be the same no matter how they're moving? Just what would that imply? So Einstein was so determined to make it that there not be a universal reference point. He said, I'm just gonna go out there. I'm just gonna think about this. What would happen if there wasn't a universal reference point? What if everyone could measure the speed of light themselves and it was always the same no matter how? And so he started thinking this through and he started doing these thought experiments. And I'm going to tell you, you don't need to understand why this is. It's much more complicated, but we could talk about it sometime, but not now. I'm going to tell you what he was willing to give up in order to hold on to the fact that there's no universal reference point. And maybe you guys will find this interesting. Again, I'm not expecting you to understand this. I'm just trying to give you a sense of what Einstein was willing to give up in order to stick with the notion of there's no universal reference point and that everyone's frame of reference is valid. And so he said, here's what the logical conclusions are if we say there's no universal reference point to measure the speed. So first of all, he found by doing these thought experiments that there's only one way that can work, and that is if a bunch of things that we take for granted aren't true. So what he found is that when someone's moving, their clock or any possible way that they have of measuring time goes slower. Clocks run slower, their body ages slower. You know, if they pour something, it's going to go slower into the glass. Every single way you have of measuring time moves slower. And here's the crazy part. The guy who's moving if I'm moving this direction, close to the speed of light, or I can say I'm stationary. That's my right. I can say I'm stationary. That means that the guy who's moving towards me at the speed of light, his clock to me is going to run slow. But this guy, he has the right to say, no, my frame of reference is valid. You're the one who's moving relative to me, and your clock is going slow. And Einstein's like, well, this is a contradiction. How can both people's clocks move slower relative to the other? But he worked out this contradiction. Most of us would have been like, well, that's ridiculous. We would have given up. He also found that when you're moving, things around you appear to shrink. So things are, you know, you're moving along a spaceship, or let's say you're in a car and you're moving close to the speed of light. Your car, when you were stationary, was 10 feet long, and there's a garage that was 8 feet long, okay? Now I'm in my car, I'm moving along close to the speed of light, and this garage, I have the right to say I'm motionless. This garage is moving towards me at close to the speed of light. That garage is going to shrink in length. It was 8 feet before, but it's 6 feet now to me. But on the other hand, the guy in the garage has the right to say, hey, I'm the one who's stationary, and that car is moving relative to me, and it's the thing that's shrinking. It's not 10 feet long. I measure it as 8 feet long. And since my garage is 8 feet long, I can actually close the front and back doors of this garage and trap that car in there for a brief second before, brief instant before he crashes through the other end. Who's right? There's so many contradictions here. Einstein worked every single one of these out. He refused to give up on the idea that there is no universal reference point. He said everyone's frame of reference is equally valid, and the laws of physics will always work no matter what frame of reference you're in, is with one exception. Okay, so this was insane stuff. And people today, they look at the theory of relativity, which talks about what happens when you move close to the speed of light, and it's truly mind-boggling that Einstein worked this out, because it's like anybody else would have just given up and said, this makes absolutely no sense. There's too many contradictions here. This can't be right. But Einstein he wouldn't give up on Galileo. He said, there's no universal reference point. I'm sticking with this. Okay, so that was an aside. I don't expect anyone to know that, but do you guys think that's at all interesting, that time moves slower when you are moving fast? Things around.
That's why you can't break the speed of light.
Yeah, and it's really insane stuff. But anyways, back to what we're talking about. So this is a really, really important concept in physics, and all the physics that you learn will be centered around this. In fact, a lot of times people say physics is the study of motion, because this is really a fundamental understanding. Now, I've been telling you guys that there's one exception to this rule that everyone's frame of reference is perfectly valid. But in order to explain that, I have to talk to you about a couple of terms so that we're all familiar with them. So I'm going to share my screen again. And I'm going to go to the whiteboard and share that. And hopefully I can clear the whiteboard. They're all drawings. Okay. So we're going to talk about three different things. The first one is distance. The second is velocity. And the third is acceleration. Okay. So if I say, how far is it from me to my front door, which one of these three am I measuring?
Distance.
Measuring distance. And what units do I use to measure distance? Just throw some out. There's a bunch of different units I could use.
Yards, meters, nanometers,
Light years.
kilometers,
Inches.
Yards,
Miles.
radiuses,
meters, light years. Did someone say miles? Okay.
Yes.
solar radiuses.
Well, I see what you're saying. Okay. Now let's do velocity. Now, most people, when they hear velocity, the term velocity is not a term most people use. What term do we normally use when we are trying to describe how fast things go?
Speed.
Speed. We usually say speed, okay? So here's the difference. In physics, there's a big difference between velocity and speed, and I'm going to just real quick explain what that is. So speed is how fast you're going. Give me some units that we measure speed in.
mph.
Miles per hour. What else?
Meters per second.
That's a good physicist right there. Meters per second, because physicists don't like miles per hour because it's not metric.
Can you measure your heart rate? So beats per minute?
So beats per minute is not a velocity. That's something that happens per unit of time, but it's not a distance. So beats is not a distance. So in other words, you have, I'll do it up here, you have beats per second. Velocity has to have a time unit in the bottom, and it needs to have a distance in top. So in fact, I'm going to write that here. It's distance divided by time. and beats is not a distance. So, so we got meters per second, we got miles per hour. You can picture anything you want. You can say centimeters per minute, but it has to have a distance divided by a time, okay? Now, that's what speed is. It's just a number and some units, distance units and a time units. That's what speed is. Velocity is something else. Velocity is something we call in physics a vector. And vectors are really important. They come up all the time. And vectors have, in addition to a number and some units, it also has a direction. So when we say velocity, we don't say miles per hour. We say miles per hour in a northern direction along the surface of the earth. Or we say, you know, velocity is, we're going at 3,000 miles per hour around the sun, and we're pointed towards the north, you know, we're not pointed towards the North Star, we're pointed towards Sagittarius, or I don't know, whatever. But a velocity has to have a time. It's a vector, and vectors are denoted with an arrow, okay? And an arrow shows the direction, and the length of the arrow shows the number, like how much of it, how many miles per hour. So you'll remember that when I was talking about the river, I did this. I did 5 miles per hour, and I drew an arrow. And in this, the arrow shows the direction of that we're talking about, and in this case, it's the speed. Here's the number part of it, and here's the units. So that's very different from 5 miles per hour going up. Those are two completely different things, but they have the same speed, but completely different velocities, okay?
That's really cool.
Now, acceleration is something different. So to get velocity, we said distance over time. Here's distance, and we divide it by time. Velocity is similar in the sense that acceleration is similar in that it's velocity over time. So we're gonna do this. We're gonna say velocity over time. So let me give you an example of this. Okay, so here we are. We're gonna start here at time, we're gonna call time 0. And at time 0, we're motionless relative to the earth. We're going 0 miles per hour. And then we're in a race car. So who likes race cars here? Raise your hand if you like a race car. Or just holler out. Okay, you guys, the Rasmussens like race cars, so does Jackson Allen. Okay, if I want to get to 60 miles an hour, what would a good race car, how long would it take a good race car to go from 0 miles per hour to 60? That's a real common statistic, right? If you want to brag about how good your race car is, you say, I can get there in how many seconds? What's a good time?
Like 1 second.
Wow, that would be a great time. Yeah, that would be an amazing time. Can your car go from 0 to 60 in 1 second? How long do you think it would take your car?
Longer than that.
Yeah. So right. So I don't know. I mean, I know that when I hear about race cars, they brag about somewhere in the 3 or 4 or 5 seconds, 0 to 60 in 4 seconds. That's a really good car. And when you think about it, if you're in your, whatever you are, I drive a Toyota for crying out loud. If I start at 0 miles per hour and I floor it in my Toyota, I am gonna probably take, I would say, between 10 and 15 seconds to get to 60 miles an hour. That's an acceleration. And the way we measure acceleration is we say it's velocity over time. So we say 60 miles per hour divided by 10 seconds, because that's how long it took me to do that. Now, in physics, you would never do this. You would never mix units like this. What you might say is, I want to be able to go 50 meters per second, and I want to get there in 10 seconds. So that's 50 meters per second per 10 seconds. Now, the way that you calculate that is you say, what's 50 divided by 10? Alyssa, what's 50 divided by 10? Oh, sorry, I muted you and you unmuted you. I'm sorry, go ahead, try again.
50 divided by 10 is 5.
5, and then we say meters on top, and we put both of the seconds on the bottom. Now, if you don't know why that is, if you don't know how I get from here to here, don't worry about it. But what I say is meters per second, or I can call that meters per second squared. Again, not important why I have seconds squared on the bottom. If you know algebra, you'll understand why I'm doing that. If you don't know algebra, you won't, but it's not important. Point is that this is how we measure acceleration in a unit of distance divided by time squared. So I'm going to put this over here, distance divided by time squared. Okay. Now, the last thing I want to cover today is somebody, I can't remember who, but someone says that when the stewardess pours your soda, she has to be careful that there's no turbulence. And I'm going to tell you what turbulence is and why it invalidates the laws of physics. You're sitting here in your airplane. Okay, so I'm going to erase all this stuff down here. But I'm going to leave the stuff up at the top. Okay. So I am in my airplane. This is a lame drawing, but I want to keep it to 45 minutes. I'm in my airplane, and the fact is I'm not a good artist. I'm in my airplane and I'm moving at 600 miles per hour. It's a vector. I'm going in that direction. Here's what turbulence is. You hit a pocket of wind and it bumps you up. It makes you rise briefly. So for a brief moment, you're not traveling 600 miles an hour horizontally relative to the Earth. Your velocity vector might be like this because you just got bumped up. You have just accelerated. You might still be going 600 miles per hour relative to the Earth, but that's a speed, and we don't care about speed. We care about velocity. You've ever so slightly changed your direction, okay? What if you're in a car and you're going 60 miles an hour and then all of a sudden you get to a corner, okay? So you're on this road and then you get to a corner and it bends like this and you're going 60 miles an hour, that direction. When you're done making that corner, you're going this direction, also at 60 miles an hour. What have you done to your velocity? Somebody unmute and answer. Jackson.
Shifted directions.
You've shifted directions. You have accelerated. You've changed your velocity. Now, again, I want to point out, you haven't changed your speed. You're still going 60 miles an hour. But you've changed your velocity because you've changed your direction. That means there's been acceleration. Now, as you go around the corner, what do you feel?
Gravity.
Okay, you're cheating, Jonathan. I know. Jonathan's cheating a little bit. He's jumping ahead.
Sorry.
Yeah, that's okay. Don't you feel kind of like you're being squished up against the door?
Yeah. Mm-hmm.
If you were to pour a soda as you go around the corner, what do you think would happen to the liquid as you pour it? Like you, it wouldn't pour straight down into the cup. It would be squished against the door. So this is the last point I want to make today. The laws of physics apply to any frame of reference equally. We say that they're on equal footing. We say that they're equally valid, except if the frame of reference is accelerating. So if you're in a turbulent ride on an airplane, all bets are off. You can't count on the laws of physics anymore. You have to say, well, this airplane is accelerating. I'm going to switch my frames of reference to the Earth. And then relative to the Earth, your soda is going to pour exactly the way you would expect it to. But you have to just remember that the soda was already moving at 600 miles an hour relative to the Earth when you measured it. So you got to take that into account into the laws of physics. If you're in a car, as long as you're going straight, you can pour a soda like it always would. But as you go around a corner, you're now accelerating, and you now no longer have the right to say, I have a proper frame of reference. We call it an inertial frame of reference or a non-accelerating frame of reference. Now all of a sudden the laws of physics are completely out the window. We can't trust them anymore. We've got to choose a different frame of reference. Or what we sometimes do is we say, I really, really like this frame of reference for the problem I'm trying to solve. I'm going to invent a mysterious force. So when you go around a corner, you call that centrifugal force. Now, centrifugal force doesn't exist, but it's something we make up because I want to be in the car and I want to explain things using my frame of reference. So I'm going to say, well, there's a centrifugal force and it's moving me to the right. Well, it's really not. There's no such a thing. It's just that your frame of reference is invalid. And so you've got to make up a force to explain why you're squished up against the door. All right. So that's it for today. I want to open it up for any questions and see if, do you guys have any questions about what we've talked about today? Please feel free to ask. So you're just going to have to unmute yourself and talk because I can't see everyone. I guess I can now. So raise your hand. I can see you now. So if you have a question, raise your hand about what we've talked about. Anyone have any questions? Yes, go ahead, Jackson.
So I'm reading this book on physics, and
Yeah.
the chapter.
You just muted yourself again.
Good. So it was talking about circles and centripetal force and centrifugal force. And when you're traveling in a circle, it's like two velocities combined always to make you in that direction. So your own inertia trying to go straight and then being pushed up against the car, isn't that like the illusion of centrifugal force?
That's exactly what it is. It's an illusion. So what he's saying is, he's saying you're going around in a circle relative to this, someone, we're going to say he's stationary, an observer who's not moving around in a circle. He sees you going around in a circle. And he says, and what he's trying to say is that there's a force that has to keep you in that circle. But to someone who is moving in that circle, he has an illusion of a force. It's a made-up force because he really wants to keep his frame of reference, and his frame of reference is invalid because he's accelerating. But he has an illusion of something that's squishing me up. Like there used to be these rides that would spin you around in circle. I don't know if any of you have seen those rides, but you feel pressed up against the back of your seat. Okay. Well, that's an illusion. There is no force pressing you back in your seat. It's just that from someone who is sitting motionless, observing this, that person has a tendency to move in the same direction. We're going to come to that in a couple of weeks. And so that's really what they're feeling. The whole idea of there's a force pushing me back into my seat is an illusion. So Jackson, if you have like specific questions, I'd be happy to answer them. Anyone else have any questions? Okay, if not, we're going to end for today. Jackson, did I answer your question? Or if you have a specific question and everyone else wants to bail, I know Jackson's reading ahead in physics, so he might have do you have any like specific questions that I could answer real quick here?
No, I don't. I just wanted to mention that.
Yeah, no, that's a great question. We'll come to that in a little bit. All right, you guys, good to see you. I have next week off, so we'll probably have another talk sometime during the week, okay? But thanks a lot for coming. Appreciate everyone's participation. Talk to you later.
Thank you.
Okay, bye.
Bye.